Okay, welcome back, students. I see Tyler's with me. And we got a good crowd. Julian, Brian, Braxton, Alex. Good crowd. Let's see who else we got here. William, Bryce, Tyler, Taylor, Reagan. Good going. Okay, we've got our class now. And we're in thermo. This is the 27th of Octubre, 27th of October, 2020, and we're in thermo. And I thought maybe you needed some help with this 549. And I thought I'd help you if you wanted me to on 549. I wonder if I could scoot that to where you could actually see it. Well, I don't know if you can see that or not.
Professor, we can see it good.
You can see it good?
Yes, sir.
Great. This was 549. It was a Carnot cycle. Let me see what the book says here. If you want me to, I'll be glad to go over any part of it with you and show you where these numbers come from.
Can you go over the P1 and V1 numbers?
Yeah, sure. Let's do that. We'll do the P1 and V1. First of all, though, let me circle the stuff that was given to start with. All the temperatures are given, guys. They gave us these 600 and 300. We know all those. The heat added at the high temperature is 250. That looks like 2500, but that's supposed to be a Q right there. If you can read my writing, that's supposed to be a little Q. Oh, come on. A little Q. There we go. That 250 was given. So we could circle that. I showed you last time where this 125 came from, but I'll be glad to show it to you again if you want me to. Just speak up. Yeah, let's show you where that came from. What you need to do is draw the schematic. In fact, some of you didn't get 4s on your homework because you're not doing what I want. I want you to draw, in this case, this would be clockwise, because this is a power cycle. And see, what you got here is QH, and this is QL. This is your low temperature, 300 Kelvin, and this is your high temperature, 600 Kelvin. And this is going to be your net work per mass. What that's going to be is the total. If you add all these up, you're going to get 125. This is going to be 125. That's the net work. It's the total of all the work per mass in kilojoules per kilogram. And see, what this is given. That's the 250. If you have 250 coming in, 125 going out, and so this here is 125 of heat transfer per mass to the environment. Now the way I got that, of course, I didn't have all these numbers. in there. What I did was I went the efficiency, the maximum efficiency is equal to TH minus TL over TH. There's an equation in your book like that. And if that's 600 minus 300 over 600, you get 0.5. And see, that's going to equal the actual, because a Carnot cycle is a perfect reversible cycle, and the actual efficiency is your network divided by your QH. Well, see, the QH is 250, it's given. And now you know that this is going to be 0.5 because these are going to be equal. And so this has to be the 125. That's where the 125 network came from. Did that make sense to anybody, or do I need to explain it better?
Just that last bit one more time.
Yeah, let's go over that last bit one more time. You might like it better this way. See, QH is given. It's 250. It's given in the problem. You read the problem, it says 250 kilojoules per kilogram are added at the high temperature. There it is, 250 kilojoules per kilogram are added at the high temperature of 600 K. If you can read that, that's a K there, right there. Now, if the maximum efficiency is equal to the actual efficiency, then 0.5 is equal to 250 minus Q sub L over 250. Now, if you solve that for Q sub L, you'll get 125. And because it's leaving and going out and heating up Oklahoma, it's a negative 125. That's where the negative 125 comes from. Did that help?
Yes, it did. Thank you.
Great. But now I think it was one of my excellent students wanted P1 and V1. Is that right, Mohammed? P1 and V1?
Yes, sir. B1, B1.
Okay, let's do that. Now there's an equation I showed you in this chapter. This is chapter 5. And it goes like this. Let's see if I can find it. Trying to find it here. Okay, here it is. Now, going from 4 to 1 is an adiabat, and going from 2 to 3 are adiabats. Those are adiabats. Yeah. Let me try this blue one. This blue one seems to work better. These are adiabats. So is that one. That one there is an adiabat also. Now, if you're going to go from 2 to 3, you guys all understood that. I could erase that, couldn't I? But this is what I want. I want a scheme, I call this a schematic. And the book does it differently. This is a Griffin schematic. I want you to do a Griffin schematic. Make me happy. Don't do it the way the book does it. I want it to look like this. I want you to have heat transfers in and out, work going out, in this case for power cycle, clockwise cycle. See, this is clockwise. Look, it goes around and around clockwise, doesn't it? See it? Temperature, the hot temperature goes here, the low temperature goes there. That's what I want. But now this equation that I'm talking about now to help Mohammed on 1 to 2. No, 4 to 1. You have a little room right here. Process 4 to 1. We're going to go from 4 to 1. And this equation's on page 160. I'll explain it much better very soon, but this equation only works on that adiabat. This 0 has to do with no heat transfer, and it's equal to C sub V dt over T plus R natural log of V. Okay, I'm getting mixed up here now, just a minute. What I want is the, oh, that's from 2 to 3. Now this one here is on the page 161. If you want to go from 4 to 1, that's this one here. They put an equal sign in my book, but it's supposed to be a positive sign. Positive R natural log of V3 over V2. Can you find that? No, there it is. Yeah, there's that equation on page 161. Can you find it? Wait a minute, these numbers are different. This is V1, this is V4. Okay, I think I finally got it right now. And see, this is going from the low temperature, which is 300, to the high temperature, which is 600. And we're going from 4 to 1. The final is state 1, the initial is state 4. And we'll explain that equation by and by. Okay. Now the thing is, Mohammed, you know the specific volume at state 4. Let me ask Mohammed. Mohammed, do you have this specific volume at state 4?
Yes, sir.
Yeah, look at here, Mohammed. You've got that. And what we're going to do is we're going to write this. I need the room up here. I feel cramped down there. So I'm going to just, we talked about that. I'm going to write this equation like this. 0 equals C sub V natural log of 600 over 300 plus R. Now, this problem here is air, isn't it? Are we dealing with air in this problem 549?
Yes.
Yeah, it's air. So R is 0.287. Natural log of V1 over V4, which Mohammed knows is 0.267. We could go back and find V4 if anybody wanted me to. But see, this is C sub V. I know what that is for air. It's 0.717, isn't it? Okay, guys, get your calculators and do this and find V1 for me. Get your calculators. This equation, by the way, that I wrote is on page 161. So plug that in your calculators and find V1 for me. This is natural log of 600 over 300. That's the natural log of 2. Okay, go for it. Well, I got a slightly different answer. I'm getting 0.04757 when I do this. I wonder why it's slightly different. It's awfully close. You could round it off to 0.476 and it'd be pretty close, wouldn't it? But that's how you do it. So you could change that to 0.4757 if you wanted to. Pressure. Here, let's do it. 0.4757. Now we're going to get the pressure. P1V1 is equal to RT1. So let me get the pressure there at state 1. Here goes. It's more like 3620, isn't it? It's more like 3620. Mohammed, that's how you get the P1V1.
Okay, thank you so much, sir.
Yeah. I'll be glad to do anything else if anybody wants me to. Anybody need help with anything else? Well, just to make sure that you understand, let's do this isotherm from 1 to 2. Let me make some room here, and we're going to do an isotherm from 1 to 2, and then we'll do something else. Now going from 1 to 2, it's an isotherm. And we have an equation for work per mass. It goes like this. So see, you could get V2 from that equation because we know what the work is from 1 to 2. It's 250. We know what the P1 is. It's 3620. We know what the V1 is. It's 0.04757. And we know what the V1 is. It's 0.04757. Do that and get V2 for me. Go ahead. We'll see how close I got when I did this before. Here goes. Plug that in and get V2. Go. Well, I got a V2 when I plugged that in of 0.203. Well, it rounds off the 2032. It's just what we said. See it? Yeah, it's just what we said. So you can get V2 that way. Shame on me for not putting in my units. That wasn't very nice of me not to put my units in there. But there's that Carnot cycle. Did you want any more help? Any comments or questions on the Carnot cycle?
Okay, Mr. Griffin.
Yeah.
Okay. I'm not getting that V1 as 0.4757. Can you show me how you did it?
Yeah, the V1. Now let's go through it.
Yeah.
Okay, here goes. Thank you for asking. Well, we have 0 equals 0.717 natural log of 2 plus 0.287 natural log of V1 over 0.2688. Where did the 0.2688 come from? I got confused.
It's the V4.
Oh yeah, we're going from 4 to 1. Yeah, okay. All right. Now I'm going to do this on my calculator now. And one tiny minute, 0.717 times the natural log of 2. This number here is equal to 0.49699, blah, blah, blah. When you put it over here, it makes it a minus 0.49699, blah, 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 equals 0.287 natural log of V1 over 0.2688. Okay, now I'm going to divide by 0.287. Here goes. 0.287. I'm getting minus 1.731 blah, blah, blah equals natural log of V1 over 0.2688. Okay. Now what I'm going to do is I'm going to hit the e to the x button. I'm going to push that e to the x button. Here goes. And what it gives me is 0.17699. That's good enough. Equals V1 over 0.2688. So I'm just going to multiply. V1 will be times 0.2688. I'm getting 0.04757. Mohammed, did you follow me on all that?
Yes, sir. Thank you so much. Thank you.
You are so very welcome. Are there any other questions on that Carnot cycle? Well, okay, I guess we'll say goodbye to that Carnot cycle for right now. And just say sayonara. There it goes. Well, I'm going to erase this unless you have a question. Here goes. Okay, we're going to say goodbye to the Carnot cycle. Now we're going to get into chapter 6, but before we do, it's really based on something called the Clausius inequality. You'll find this on page 167. It's called the Clausius inequality. It was discovered, oh gee, over 150 years ago. And you're looking at it. That's it. That's the Clausius inequality. It's on page 167. It was discovered by examining steam engines. I should have left all that stuff up there on our Carnot cycle. I'll demonstrate it for you. But first, we're going to break this Clausius inequality into two separate inequalities. Clausius did studies on steam engines. This was the age of steam. This inequality is either equal to 0 or it's equal to less than 0. Well, one of these is going to happen. That's what that sign means. It means less than or equal to, right? So it can either be less than or equal to. Now what this circle means is a cycle. We're dealing with a cycle. Now on our cycle we just did, on our Carnot cycle, it would be one of these. This would equal 0. This is what you get if you have a reversible cycle, a cycle that runs perfect. This is a reversible cycle. This is an actual cycle. In an actual cycle, the sum of all the heat transfers divided by their absolute temperature at which the heat is transferred throughout the whole cycle will be less than 0. It'll be equal to 0 if you have a perfect cycle. Let me demonstrate that with you with the values from your Carnot cycle that you, I just had them on the board there. But remember, from 1 to 2, going from T1 to T2, we had a heat transfer of 250. It was a positive 250 kilojoules per kilogram. Actually, what they're doing is little letters here. You know how that works. The big Q is equal to the mass times the little q. But you could put little q's in everywhere and it'd be fine. Now the temperature at which that heat transfer took place was 600 Kelvin. Now we're going to go from state 2. We're going to go from 1 to 2. Here, let me just write it this way. We're going to go from 1 to 2. And here we're going to go from 2 to 3. But see, there is no heat transfer from 2 to 3. 2 to 3 was an adiabat. So you have 0 heat transfer, and the temperature varies during the transfer. But whatever the case is, since you have 0 heat transfer from 2 to 3, remember, that's the adiabat. Then going from 3 to 4, I think you had a minus 125 kilojoules per kilogram at 300 Kelvin. And then finally you went from 4 to 1, but see, that's going to be 0 again, because from 4 to 1, remember, on your Carnot cycle was an adiabat. Now, if you add all this stuff up, you're going to get 0, because 250 over 600 minus 125 over 300 will be 0. If you don't believe me, put it in your calculator. These are both 0, so you can forget them. Those are your adiabats. I think you can see it. If you have a reversible cycle, this is what you get. Now, if it's not reversible, if it's an actual cycle that has what they call irreversibilities, then it's not equal to 0. It'll be less than 0. Now, here's the interesting thing. Anytime you have a cycle where you have a quantity here and you add it up for the whole cycle and it's equal to 0, then whatever that thing is going to be a property. Like, for instance, let me show you some examples. If you were to add up all the changes in temperature for your cycle, going from 1 to 2, that's an isotherm. There isn't any change in temperature. Going from 2 to 3, that's when you cool off. The temperature goes down, but it's an adiabat. It's an adiabatic expansion. You cool off 300 degrees Kelvin from 600 to 300. See, this is going from 1 to 2. I probably should write that out. This is from 1 to 2, dq over t. This is from 2 to 3, dq over t. This will be from 3 to 4, dq over t, and that's 0 because that's your other adiabat. And finally, this is the integral from 4 to 1, dq over t. And that is back to plus 300k. And you'll get 0. See, the change in temperature, if you go around a cycle and you come back to where you started, will always be 0. In fact, the change in a cycle of any property like pressure will be 0. Or specific volume will be 0. Or specific enthalpy will be 0. It kind of makes sense because you come back to where you started and you darn well better have the same property at that state that you started with when you get back to it. I don't know if that made sense. But here's the bottom line. If this thing is equal to 0, then this thing here must be a property. Now the catch is it's got to be a reversible cycle. But if you have a reversible cycle, this thing here is a property. They decided to give it a name. They call it the change in entropy. They use the symbol S for it. And it's equal to the heat transfer at the forgot what I was going to say. At the temperature of which the heat is transferred. Heat is always transferred at some temperature of the boundary. The boundary between usually it's the warmer body it's always the warmer body is transferring heat to a cooler body, and the boundary is that temperature there. Like from 1 to 2, the temperature is 600 Kelvin. They defined this. They said, hey, this thing's a property. Let's give it a name. Let's call it entropy. And so there you have it. We have just defined what entropy is. Now, if you want to write it in little small amounts, the change in entropy for a very small process, not a big one, will be the delta Q over T. So we have our entropy change. It's the amount of heat transfer divided by the temperature at which it's transferred in Kelvin in a reversible cycle, or in this case, a reversible process. So the units of entropy are kilojoules per Kelvin. If you want to use little letters, the units of specific entropy, they call that specific entropy. That will be little q over T. T's got to be in Kelvin. And see, what that'll be is kilojoules per kilogram Kelvin. Because little q is kilojoules per kilogram. Well, we've just defined what entropy is, and they have tables of entropy. Let's go through an example of the change of entropy for water. Let's do that. Before we do that, are there any comments or questions? Okay, well, let's do that. Now before we do, we might make a note of the symbols that they're using. We said that this is equal to they use a lowercase delta. You know, in Greek, they have a delta. They have a capital delta that looks like that, and a lowercase delta that kind of looks like that. They can't go dq because that implies a difference of Q2 minus Q1. Well, heat transfer is not a property that exists at state 2 and at state 1. Heat transfer is not a property. It's something that occurs between two states. If you have two different states, you can have a heat transfer between them. And so they don't use an exact differential for that. They use an inexact differential for heat transfer. Work is the same thing. Remember, work is the integral of P dV. If you plotted up work on a PV diagram, here's 1, here's 2, here's state 1, and here's state 2. This is the amount of work that you have. You have to take the area underneath the graph. You don't have work at state 1, and you don't have work at state 2, and you don't subtract them. You don't go W2 minus W1 because there is no W2. The work that's done is the area under your graph. You have to have a process. Same with heat transfer. You don't have a heat at state 1 and a heat at state 2. It's not a property. I don't know if any of that made sense, but I'm trying my best here. Okay, now where was I? Let's see. Oh yeah, we were gonna boil some water. Now go to your table, and you know water looks like this. There you go. And let's just boil some water. We're going to go from state 1 to state 2, and we're going to boil the water. I don't know, it doesn't really matter. Boil it at 200 kilopascals. That's roughly 2 atmospheres. And if you go to your tables for water, it says here 200 kilopascal. It says the temperature here is 120.23. So let me put that in there. 120.23. See if you can find that in the back in the tables. And we're going to put some values here. State 1, V1 is, we want 200 kilopascal. There it is. It's 0.001061. So see if you can find that. And then state 2, here's state 2. V2 is 0.88573. Okay, great. So what? Well, what I want to do is I want to find the heat transfer from 1 to 2. Do you guys remember for a isobaric process, the heat transfer from 1 to 2 is equal to the change in specific enthalpy? That only works for an isobar, but we have an isobar. And you know what? In this case, that's just equal to HFG. Well, what's HFG at 200 kilopascals? You tell me. HFG. I got 2201.96. See if you can find that. Kilojoules per kilogram. Now what we're trying to cook up right now is really delta little s, and it will be the integration of d little q over t. In this case here, t is a constant. You can just pull it out. And the q, when you integrate that, you just get q. It's just q over t. We got the q, and we got the t. The q is 2201.96 kilojoules per kilogram, and the t is, we got to get it in Kelvin. See, that's Celsius. We have to have Kelvin. Okay, let's see if I can get Kelvin here. Suppose I did that right. Okay, plug that in and we'll get the change in specific entropy going from 1 to 2. Go for it. I did that and I got the change in specific entropy going from 1 to 2 to be 9.1986 kilojoules per kilogram Kelvin. Did I do that right? Somebody say, uh-huh. I'm going to wait. I'm more patient. I can just wait.
I got 9.20, but I guess that's close enough.
Well, you must have rounded something off. Let
The
me do
bottom
my
ten-
own.
My calculator's rounding that.
Oh, your calculator's running. I bet we're
Your-
fine.
Your bottom temperature, you have it as 239.38. We're adding 273.15 to 120.23, correct?
Right.
I don't
Did I
know
do
if
that wrong?
Let me add it one more time just to make sure I'm not. I'm getting that it's not 239.38. I mean, I'm getting 393.38 unless I'm
Oh, this is wrong. This is wrong. This is wrong. Thank you for speaking up. It's 393, isn't it? 393. Now let's do it. Let's do it right. This was wrong. But I think that's right. Okay, let me try it again. There's a dot right there. Uh, 5.5975. How's that? That better?
Uh-huh.
That's what I like to hear. Now I want you to look. The change in specific entropy in this case should just be SFG. Look and see what it says for little s, FG at 200 kilopascals. What does it say? Let's see, little s. It says, boy, Jove, it says 5.5970. That's pretty close to what we got. Pretty dang close. I don't know why we have a slight difference there, but it's pretty dang close. Guess what? That's how they got those values. That's where those values come from for specific entropy. Okay. Well, now that's on a PV graph. Now let's enter the exciting world of TS graphs. I just need some room here. In this chapter, now we're talking about chapter, what's the next chapter that we're studying? Chapter 7, is it? I think it is. I think we've been in chapter 6. But see, chapter 7, no. We've been in 5. We've been in chapter 5. That Carnot cycle was chapter 5. Chapter 6, they're talking about entropy, and they told us what it is, and I see some equations like I just wrote for you. But I want to talk to you now about TS diagrams. We need a TS diagram. Here we go. And now these occur just like the PV diagrams. You can have them for an ideal gas, or you can have them for things like water. See, if you have water, then you have a vapor dome. There you go. Da, da, da. It's just that the vapor domes are some more symmetrical looking for a TS diagram. But here, let's do one for an ideal gas too. So if you had water, it would look like that. But if you had a ideal gas, you don't do a vapor dome. You do some isotherms that go like this. These would be the hot ones, and these could be the cold ones, but they'd just be flat like that. Whereas, remember how isotherms went on the PV diagram? The isotherms came down here, they went over and they went down. But see, this is a TS diagram. Now let's do isobars. Now isobars are kind of weird on a TS diagram. They come up here like this. Then they go over like that. Then they come up here. Now this would be a high pressure. And here isobar here comes up here like this. And the isobar goes over like that. This would be the pressure at a low temperature on something like water. But now, like if you did something like air or helium or some other gas that behaves like an ideal gas, here's how your isobars go. They go like this. Here would be the high pressure. And here would be the low pressure isobars. Okay, well, there's enough theory there. Why don't we try working a problem here? That'd be good. What equations do I need for that? Well, I'm going to need these equations here. I can see them. But this is what we're going to learn to do. We're going to learn to do TS diagrams. Now I'll tell you why. I'll tell you why they're important. If you have this equation here, we know we can write it like this. Do a little algebra with me. I don't want the capital, I want the lowercase. I know you can get from here to here. This is really a definition. Now, if you want the total heat transfer, can you see that it's the integration of your TdS? You know what that is? That's the area under your TS graph. Like for instance, if you wanted to know the heat transfer between here and here, it would just be the area underneath this graph. It would be that's your total heat transfer. I need small letters, sorry. It's the area under your graph. If you wanted the heat transfer up here, say from here to here, well, we can do that. Let's do that. That would be this area here. Why are TS diagrams important? Well, they give you the heat transfer. The area underneath the TS diagram gives you the heat transfer. Now, the same thing is true over here. The same thing is true. Like if you wanted to go from here to here, for example, now that's traveling along an isotherm, say from 1 to 2. And the heat transfer will be the area, well, the heat transfer per mass. Okay, well, that kind of makes sense. Now what do you use if you're dealing with things like water or refrigerants? You use the tables. But what do you use if you have an ideal gas? Well, we have equations for that, and they begin discussing that on page 181. And here's our equations. And I want to show you where these came from. I need to work some problems. Hang on a minute. Maybe we should work a problem first. Let me dig around here and see what problem I want to work. And we're in chapter 6 now. We're moving on, and we've talked about entropy and the TS diagram. Okay, here we go. We're going to do this problem. Gee, I hope it's not on your homework pile, but I forget what your homework is. Let me look this up. Let's see what your homework is. Today's the 27th. And no, this one's not on your homework. We're going to do problem 619. They've got water, so we're going to use our tables at 400 kilopascal with a quality of 0.25. And we're going to raise the temperature to 20 degrees Celsius. In an isobaric process. And they want us to find the change in specific entropy. Okay, I bet we can do it. Now, what we should do is a PV and a TS diagram. Why don't we do both? That'd be good. Here's our PV diagram. And 400 kilopascals, 25 Celsius, that's kind of in here someplace, or 20.25 quality, that's kind of in here. Here's state 1. And this pressure is 400 kilopascals. And we're going to go in isobar to 20 Celsius. Well, what is this temperature here? Now, you guys all have tables. I want to know what this temperature is right here. I'll shut up, and I want you to find that temperature at 400 kilopascals. Go for it. Somebody that knows how to find stuff in the tables. How about it, Bryce? Unmute and say hi.
Hello.
Can you get to the tables, Bryce, and find out what this temperature is? What is it?
In Celsius, it's 143.63.
Good going. Good going. 143.63 degrees Celsius. Now we're going to follow an isobar, and we're going to go to 20 degrees Celsius. Now where the heck is that? 20 degrees Celsius? Are you kidding me? That would be a lot colder, wouldn't it? Well, we're going to have to do this, aren't we? See, aren't we going to have to go from 1 to 2 like this? See, 20 degrees Celsius is colder, right? There's 20 degrees Celsius. We're gonna have to do that. Okay. Now they want to know what the change in specific entropy is. Well, I think we can do it. You have to use the tables. We're going to get S1. S1 is just like you're dealing with it's just like when you deal with V1. See, V1 is VF plus the quality VFG. We've done that before. U1, if you wanted little U1, that's UF plus the quality, hope you can read my writing, times UFG and so forth. Well, the same thing is true here. Now we need to look that stuff up. What is SF at 400 kilopascals? I don't know. It is 1.7766. We're going to find S1. There we go. Now those units are kilojoules per kilogram Kelvin. And then we have to go 0.25 times SFG. Let me help me find that. 5.1193. We can get S1. Now, how are we going to get S2? Well, S2, that should have the same specific entropy as the specific entropy at 20 degrees. That's 20 degrees right there. And at 20 degrees, we're going to have to shop around. At 20 degrees, the specific entropy is 0.2966 according to my tables there. 0.2966. What that is SF. The specific entropy at 20 degrees here should be the same there. It's just got a higher pressure is all. And so I think we can get delta S. Let's see if we can. Let me get my calculator out. We're going to find out what S1 is. I wonder if I did that right. I'm getting 3.0564. And then when you subtract that, here's what you get. I'm getting 2.7598 kilojoules per kilogram Kelvin. Now I wonder if that's what the answer book says. Let me look this up. This was problem 619. And okay, now wait a minute. I did something horribly wrong here. Oh, I didn't read the problem right. T2 is not 20 degrees. It's raised 20 degrees. Let's start all over again. We're going to rate, it's delta T is 20 degrees. I thought they said T was 20 degrees. If you read the problem, though, it says the temperature is raised 20 degrees. Okay, well, what was the temperature to start with? Well, it's 143.63, right? So T2 is not 20 degrees. It's 163.63. Sorry about that. Okay, now how are we going to find the specific entropy there? Well, we know the pressure, it's 400 kilopascals. So we're just going to go to 400 kilopascals. I went the wrong way, guys. We're going to go this way, and we're going to go out here until we get to state 2. I went the wrong way. I read the problem wrong. And what we got now is 163. This temperature is 163. We went from 143 to 163. And that's in the superheated vapor. So we've got to go to the superheated vapor chart at 400 kilopascals. Now help me shop around and find 400 kilopascals. I found it. And what we want is 163.63. Well, it's in there. I think we can do it. But it's not going to be pleasant. Well, let's see if we can. How are we doing on time? We got 10 minutes. I bet we can do it. Let me make some room. Make it over here. There's some room over here. We're doing 619. And right now we're trying to find water at 400 kilopascals at a temperature of 163.63 degrees Celsius. Okay, well now here's what they said. Got lost there. Water, 400 kilopascals. And what we need is 163. Well, they don't have 163. I'll tell you what they have is they have 150 degrees Celsius and they have 200 degrees Celsius at 400 kilopascals. And what we're after is a little s, see? The little s is 6.9299. And at 200, it is 7.1706. And see, what we want is 163.63. We have to interpolate. This will give us S2. We've got S1 here. It's 30564. We got that. And we can get the change in specific entropy. Since I'm running out of time as usual, let me just tell you what it comes out to be. It comes out to be 6.99. You can do this at home and see if you agree. So looky here, we've got our S1 on. We have S2. It's not this. I did that all wrong. I read the problem wrong. I went the wrong way. S2 is 6.9955. So our change in specific entropy is, well, you subtract those, and here's what you get. You get 3.9391 kilojoules per kilogram Kelvin. We just did a problem with water. Found the change in specific entropy. Now let's do the TS graph. That would be fun. We have a lot of info here. We have our delta S and our S2 and our S1. We just need some room. Here, let's do it up here. Okay, here we go. We're going to do a TS diagram. Now remember, it's more symmetrical looking, kind of like that. It's kind of like Mount Fujiyama. It's a perfect volcano, okay? Put a little snow on the top there. Round that off prettier. There we go. There we go. Now, let's put in our 400 kilopascals. Well, remember, isobars go like this. They come up, they go over, and they come up. That's your 400 kilopascal isobar. Now we're at, what, 25, somewhere in here. X is 0.25. And we're going to follow an isobar, they said. Well, what we're going to do is we're going to go from here at state 1. We're going to follow that isobar, and we're going to come up to here to state 2. There's our process. It's an isobar on a TS diagram. And we could label these. See, S1 is 30564. And S2 is 6.9955. So we got that label. We know what this temperature is there. It's that's the 163. No, that's the 143.63, and we know what this temperature is here. That's the 163 degrees Celsius. See, it went up 20 degrees. So we've entered the exciting world of TS diagrams. Any comments or questions on that? Okay, now here's what I'm going to show you next time. We don't have time right now. But next time, I'm going to show you what you do when you have an ideal gas. See, this is not an ideal gas. This was water. And when you have water or a refrigerant, you have to use the tables. And we know how to do that. But when you're dealing with an ideal gas, here's what you'll use. These equations are on page 183, and I want to talk about them next time, but we don't have time now. What these are ideal gas equations. And one of them goes like this. This might look familiar. In fact, we had this equation. This is on page 183. We had this equation, but this was 0. We didn't know that the change in entropy was 0 going from, well, that was the adiabat. Actually, it wasn't from 1 to 2 on our cycle, it was from 2 to 3. This is the change in specific entropy going from 2 to 3. You'll see that equation on page 183. I'm going to talk about it next time. But we could also do it from 3 to 4. No, from 4 to 1. Right? Yeah, from 4 to 1. And that would be the integral from 4 to 1. I think we did this, I think I did this equation for Mohammed to find V1 because remember, he knew what V4 was.
Professor, is that plus R log or minus R log? And is it CP or CP?
This is CV. Now there's two other equations that I'm going to talk about. We only have a minute left. That go like this. And they go the integral of well, you could do the same, adiabat. That'd be okay. Only it's CP. Thanks for mentioning that. But see, that's a negative. But here, these are not specific volumes. They're pressures. Okay, I'm getting fouled up here. If we're going from 2 to 3, this needs to be 3 and this needs to be 2. This is going from 2 to 3. And do I have room to write the last one? No, I don't. My time's up. This is going to be the topic next time. What do you do when you have an ideal gas? You don't use the tables in the back. You use these ideal gas equations. Well, we ventured into some new, read your book, do your homework, and I will see you on Thursday, right? Today's Tuesday? Yeah. I'll see you on Thursday, guys. Adios,
Professor.
muchachos. See you later.
Yeah.